What's the best language for compiler? I think it's a question that gets asked pretty much by every kind of new person starting off. People kind of have this obsession with like, what's the best language for this? What's the best language for building a game? What's the best language for building a compiler? And the answer is simply, TLDR. There is no best language. It's just whatever one you choose. But there's typically more sensible languages. Like I wouldn't write a compiler in assembly, and well, just probably verbatim. Um, and I probably wouldn't try to write a compiler in SQL. Um, SQL would be a bit of a more difficult choice, I think, than assembly to a degree. But yeah, and I think it comes down to the fact that, well, no, maybe I don't know, it doesn't really matter. When you're looking at a case like, I guess SQL, you just like build the string. Like, anyway, that's off point. When you're looking at a case of what's the best language, it really typically doesn't matter. What typically matters is kind of the person trying to build the language, whether or not they're skilled enough, and also just kind of the general language idea, I think. Some languages are easier to build than others. Like Python is probably not a great decision to build a language in, mainly because it would struggle with the type safety that you would kind of need. I mean, you can still kind of do it, but it won't be as nice. And things like switch cases are really convenient to write in languages. And Python just doesn't have switch cases. And you can use dictionaries and stuff like that, but it's not the same. I think you could do it, but I really wouldn't choose a language like that. I would probably do something like, unless it's like a really simple kind of assembly-like language, I would probably go for, more of a modern language. I don't mean more of a modern language, sorry. I mean more of a statically compiled language, something like C++, Rust, Zig, Odin, all that fancy stuff. Even C sharp would be fine. And I think honestly, it's mainly just having the flexibility in the language to kind of define that sort of stuff would be much nicer. Um, So I don't necessarily think Python would be bad. It would be slow though, and I think that's a big thing about compilers is they really should be fast. And a common problem nowadays is actually compilers are perceived to be much slower than they really should be. I mean, how many times have you compiled JavaScript and you've waited like 100 billion hours for goddamn JavaScript to compile? And I know there's a thing called Vite that was written in Rust, but I still believe that that's like infinitely slower than it has to be because fundamentally compiling JavaScript really isn't that difficult. Well, that's like a Babel kind of thing. But anyway, I say compiling JavaScript. I mean like bundling it, minimizing it, that kind of thing. Webpack effectively. Doing that sort of stuff isn't really that difficult for a compiler to do. It's nowhere near the difficulty of things like optimizations and stuff like that. But it could be entirely just due to the quantity. And that's thing that's always going to impact compilers and especially minimization algorithms is when you reach a high quantity of input, um, they do start to struggle. And so that's kind of an interesting point here. Compilers scale very weirdly in terms of performance. Um, because it does kind of hit, there's like certain points where you have there's so much data going through your system, it's just like gigabytes worth of RAM, right? And that's basically a problem with things like Chrome and stuff, right? um, but typically there's a few really interesting things about compilers anyway, but I'll go into that a bit later. I want to begin, not today, basically. And so what I want to do is I want to begin with breaking down into a series of segments. And this is going to be quick, hopefully not particularly long, but I do kind of want to pay a lot of attention to certain parts. And more importantly, I want to show off some real examples. So the first thing I want to start off is effectively talk about what I like in C++. And I would say I do have some examples that I'll show, but I kind of want to stop and talk about a bit of history. So I've written quite a few compilers in my day. I finished quite a few ones were just left and never finished. Um, and typically, the thing I always liked about C++ was the fact that I kind of had a lot of flexibility in the language to do whatever the hell I wanted. It's not like Java where your opera overloads don't exist. Um, you really can't do things like implicit casts. There's no such thing as templates. Generics are kind of really limited in Java. And so with those kind of languages, it's kind of hard to kind of really bend the language to your will, and you kind of end up writing very verbose code. We're saying like C++, even though it's still pretty inflexible, there's still a lot of room to kind of bend things. And so you're able to kind of build the language that you want out of the kind of remnants and ruins of a 1980s language, right? And Rust pretty much has the same kind of concept there, I would say. They both kind of approach the problem in the same way, kind of giving you a nice foundation, and then you build upon that foundation to do really what ultimately you want in the end. And so if I kind of start off with a point, and it's all about templates. This is probably my one big gripe with C++, and one of the reasons why I'm not using C++ nowadays. And I'm opting for C# or Rust, depending on the circumstances. Rust, where I kind of care more about performance, and C# where I care more about productivity. And it kind of comes down to a pretty simple thing, and that's the complexity that there is in compiling templates. And so let me just show you an example. Switch over to the scene. And so what we have here, right, is we have a pretty simple example of source code that we're then compiling through some lector that's basically splitting up into a sequence of tokens. So this system comes along, goes, oh, there's an int, and it's a plus sign, and there's another int, then it's a multiplication, and then there's another int. And then this is then going to be constructed typically into some sort of AST, which pretty much looks like the original source product, but it's kind of in a structure that the compiler can kind of understand better. And then typically this gets lowered down into some kind of alternate form. So for example, you may have like a high level intermediate language. I was going to say instruction register. I don't know why. Intermediate representation, right? IL, IR, it's the same thing. So IL typically means language, IR means representation. But this is pretty much the same thing. So you have some kind of high level intermediate representation. Someone's just got 8 here, it doesn't matter. And typically this kind of represents your code in pretty much a different form. And so in this case, it may literally just be a series of instructions, something like, push int, and then I guess I would do comma. And then you would have like, I guess it'd be like push int 1. Then it'd be like push int 2, push int 3, operated multiplication, operator addition, right? And this is like some kind of like stacked based system to do like some series of stack operations to manipulate this. Now this is, let's be real, this is much lower level than high HIR. So this is probably pretty much your bytecode. This is kind of more like your final product, but that's kind of the idea. Your higher level would probably not be like this. It would simply be almost like code. It'd be like a series of instructions that would care less about pushing ints and would be more caring about like registers and stuff like that. This is more of like the stack based. But it doesn't really matter, right? The idea still remains that you're kind of lowering it down to a simpler form. And so the problem with templates comes from the fact that templates originate in the middle between these phases. It originates at some phase called semantic analysis, right? And semantic analysis is effectively where we add things like types. It's where we validate your code. It's basically just a ton of things, right? But they're the two kind of major points. I guess validation is technically what I really want to say here. No, it doesn't even matter. There's a bunch of stuff that semantic analysis does, but typically the point is to basically validate whether or not your code makes not so much just like, it's not so like when you pass it to create the AST, this is like the passing stage, passing into an AST. This is typically where we kind of validate the structure of the program. This is more where we validate the behavior of the program. I guess is kind of the way to distinguish the two. And the problem with templates is templates kind of do a lot of their work in this kind of CMA step. And what I mean by that is if you have a template like vector, right? And this is the template class for vector. It has a ton of stuff in it. It has a sub template for some VB val. Has this is the Microsoft version of it, but typically they're all the same kind of idea. Now these are friends. This just means that this thing can that these classes can access this basically. So this is not data. It does look like there's pretty much no data stored directly. It would be somewhere else, I presume. Maybe like in some private member somewhere. But there will be data somewhere. Oh, you can see there's like an iterator here. Some kind of iterator. There's a bunch of stuff here. I'm sure if we scroll down. Oh, here we go. This, no, that's resize. My data. Where the heck is my data? My pair. Here we go. This kind of looks like it, maybe. Maybe I scrolled too far, but that also doesn't really look like it. Anyway, it doesn't really matter. So you kind of have some kind of vector, right? And this is basically just like an array that grows over time. And the problem with this is that this vector, in terms of like compile time performance, sadly, interesting. Sadly, it doesn't really have. How do I put this? It's not particularly clever. And it basically originates due to why it was created. So templates were effectively created because they wanted some way to kind of handle the case where you had these kind of common containers, right? Common containers, common functions, like a way to handle that. And so, the idea was, oh, okay, we can introduce templates, and templates are great. They can do all this awesome stuff. We only have to write one array, right? It's very flexible. But they work based upon the idea that you only have to, though they work based on the idea that you have to compile them for every single unique type combination. And that sucks, like real bad. Because when you have to compile them for every single unique type implementation or type combination, permutation, whatever, right? It means that you're actually like reinterpreting this entire class and all of its subclasses and everything related to it, everything that you ever touch, you're reinterpreting, right? For every single construction you make. So if you do one of ints and one of doubles, that's two completely separate templates. It has to be, because you can actually decide on how the template's created based upon its types. And that is a fundamental issue when we talk about compile time performance, because it makes them basically Turing complete. You basically have an entire language that sits within templates. It's literally like an entire programming language within templates. And that's a huge issue to me, because it's slow as hell. Because it's not a real language, right? It's not optimized, it's not converted, it's none of that. It's runtime focused, it's kind of fake, and it really suffers from this idea called SFNIA, right? Which I never got to remember what it means, but I think I even spelled it wrong. SFNF. No, that's all right. And it basically means substitution fail is not an error, right? Pretty big concept in C++. And it's pretty much the fundamental reason why we can have things like this, where we go, hey, these types have to be the same. Where we can do all these kind of crazy, it's pretty much the reason why, things like concepts exists. That's fair. I should be trying to save vector. I guess I'll just like undo it. The reason why concepts exist, the reason why it writes slow, the reason why kind of templates are so insanely crazy these days, right? All really comes down to that idea. Someone's like, oh my god, we can do this with templates. Like when they wrote templates, they didn't really realize these things were Turing complete. And then someone was like, haha, they are, right? And I think typically in most cases, especially now, I feel like if someone found that, everyone would be like, oh, that's really cool. but you really wouldn't see like the entire community go, oh my God, we have to start using this. Because what typically would happen is the language designers would go, oh, people really want this. Let's implement a proper feature that does this, that considers the runtime performance, that considers the compile time performance, and actually does this properly. But that didn't really happen with C++. So suddenly what you had is you had people go, oh my God, we have this way of doing these things that we love. Aha. And the STL was born. The standard template library, effectively. It may be born before then, but it kind of really came into fruition due to Sifine, or however you want to say it. And so suddenly that's really, really big problem for me, because it's just the wrong approach. And it's kind of, I think, sad in some ways, because I think C++ really is a beautiful language that has such a good opportunity of something kind of coming out of it and something being really nice and great coming out of the language itself, but it suffers fundamentally from this, I think, because it's held behind. It's much more complex to write code for because of constraints like this. It's slower to compile, significantly slower. I mean, compiling goddamn Chrome is insane. Google bans templates in a lot of cases because of the fact that they're slow, amongst other reasons as well. But they're also impossible to debug. Like, it's so annoying the compile errors you get from them, that you can get compile errors that are hundreds of lines long, right? And that are very hard to read, because the thing is that templates are the lowest level denominator. That's the errors you get. You get the lowest level denominator, which means even if you have someone in your code going using string equals and then some really long line, right? It doesn't matter how long this line is. It's not going to say string for your type. C++ will say this, because that's really what it is. This is just some alias. And C++ goes, I don't care that you're using some alias. It's really just this. I'm just going to tell you what it is. It's kind of almost like C++ was built for people who like to write standard library code, which I think is actually kind of accurate, because it's really nice to write like standard library code, I'm sure, right? Because, oh, it's also, everything's so explicit and stuff like that to a degree. Like, I mean, the fact that everything has to start with a goddamn underscore makes half this code so unreadable. This is like another big problem, is that it's very hard to read like the source code for anything, because look at this. Like, you're really telling me that this code is necessary. My pair dot my value dot my first. What the hell does this mean? Like, you're really telling me that you can read what any of this code does? It's a vector. I mean, first year students do this, right? I expect first year students in every course I've ever taught to be able to do this. And this is the code that's written. And it's not the fault of the code writers. It's the fact that C++ has such weird constraints and things, right? I mean, some of these names, to be fair, are their fault to a degree. I mean, it's various other things too. But like, you first, you last. I mean, it's to a degree. Come on, but like, it's still kind of insane. All these like really weird names, right? And so this is pretty much kind of where my major problems lie with this entire thing. Is I just think that they approach the problem wrong. And it really sucks, because I think they had a great opportunity with this stuff to check that it's correct, but they didn't. And so really it kind of comes down to this. If I wanted to use C++, I would really feel like I'd have to write the standard library again, and use my own version of it, and make it very simple and very clean, and use very few templates, and that's where it's needed, and not have 1,000 nested templates and stuff like that. Um, and I feel like that would help compile errors. It would help a whole lot, right? But it's a whole lot of extra work just to write a programming language, and it also makes it really hard for other people to contribute, because suddenly I wrote my own language and my own standard library. So not only are people coming in and having to like learn how the compiler works if they want to contribute towards it, they also have to learn how my standard library works, which is a lot of extra barriers. Um, so when I look at like something like this, it really comes down to the fact that templates are evaluated in like after, like, but basically before this step. So if you compare this to like a language like C#, which has generics, right? Generics in C# are like first class. They're not just like copy paste each variant, which means they're slower, fair, but because they're basically virtual. The benefit is that you can really just compile the code once, right? You're not compiling code 10 different times. And the other benefit is that you're pretty sure what the code's going to do, right? The code isn't going to fail to compile because the restrictions have to be defined prior to use. And this actually comes down to my second big problem of C++ templates. And that is that templates are optimistic. And I think if they actually did concepts first with C++, and they made concepts a requirement, so you had to do concepts to get any types in there, I actually think C++ would be fine with templates. For in terms of error messages, and I think in terms of use and in terms of a lot of things, not perfectly fine. I think compile time speeds would still be a problem and other problems, but I think it would be much better. But because templates are optimistic rather than, I guess, pessimistic, right? It means that you end up in a situation. This is 1S? Yeah. I don't know. It doesn't really matter. But you end up in a situation where basically the C++ compiler gives you too much rope. And when you break its rules, it doesn't know how to deal with it. For example, in C++, if you define some generic, like some, I don't know, let's say some add function, right? This won't compile. Because it goes, hey, I know you're trying to add A and B, but A and B is just some generic. Who's to say they even have a mathematics on them? Now, in the latest version of C++, C++10, you can actually define a constraint, and I don't actually remember what it's called. Maybe it's called like numeric or something. But some kind of constraint that lets you actually do this. But that was only in C++20. Before that, there was no math operations. Now that's your fault, C++, to be fair. But up to that point, there wasn't. But what you could do instead is you could do really anything that you can do with a type. You could say, hey, where T is any type of my choosing. So T can be any, I don't know, any jumpable. So this means that basically T is like a real concrete type that inherits from I jumpable. Or T is any class. Or whatever. But these are real types. I can do whatever I want with them, right? I don't have the same flexibility as C++. Which means if I give a wrong type to this, if I give a type where this isn't valid, it's going to fail. So if I give you a struct, it's going to fail. I can't just go add 5 and 5. No. Sorry. Oh, jeez, that was a bit bad. I can't go add 5 and 5 because it's not a class. I mean, again, add is probably a bad term for this, but whatever, you have to do. Right? I could do, foo A and B because strings are classes, I believe. But I can't do 5 and 5. I can even define and say, oh, it's going to have an empty constructor. You can't specify exactly which constructor you want, sadly, but you can specify it has to have an empty one. I believe they are going to add it at some point, regardless, it doesn't matter. And then therefore I could have some kind of creation function that initializes an empty T. So this would like new T. Right? And therefore I could say, foo of, I don't know, what's an empty constructor? I believe string is an empty constructor. It's lowercase s. And therefore I can create an empty string this way, maybe. That's to me is very important. Because when you deal with an optimistic language like C++, right? You go, oh, I want a template. It's called class T, right? Just like this vector up here. Right? Here's my class T. I guess I call it a function, like, it doesn't even matter, like, I guess add. Sure. Right? I'm going to add TA, TB, then A plus B. And then it will check whether or not, given this type T, does this compile. And if it doesn't compile, it gives you an error. So rather than putting the onus on the person who creates the template to exactly specify how they want it to be used, they put the onus or the responsibility of this function on the caller, which is just crazy. So now suddenly I'm calling this function and I'm responsible for knowing what correct arguments are to pass to it, rather than being told what's possible to pass to it. I'm relying on documentation, I'm relying on reference implementations, I'm relying on everything. Reference, whatever, like examples. And that's just bonkers. Rust solves this by doing it the C# way, being pessimistic. You have to specify your constraints. You wanted to implement these three functions? Don't just call the functions. Don't just say, oh, a dot some random function b. You have to say, okay, this has to implement a trait which has some random function b. That kind of distinction between the two, I think, is very important. Now, Rust does something called macros, which are kind of like this. But the thing about macros is they occur before type analysis. And they're expanded, just like C++ macros, right? Not like C++ templates, and they're expanded, right? In code, they're like text replacement, basically. There's fancy text replacement, which makes them much better or less prone to this issue because the compilers you get are really, really confusing, but typically they're unique syntax. So it's not so much you're passing the wrong type, you're typically calling it the wrong syntax. And typically that kind of thing you need reference implementations for anyway, or reference examples, so I should say, or you need documentation for anyway, because you don't necessarily know what type to do. And so I think for a compiler, this is really kind of where my problems with it originates, is with templates and with the standard library in general. The standard library is quite bloated. It has a ton of features in it that are old and should be deprecated. It has things like, for example, file system, FS, I think it's called. There may be a slightly different prefix, which has, I believe, like 2 or 3 ways to handle errors. And it kind of sounds good from an out way. Oh, I can handle errors like Go, where it kind of returns some like result object. I guess that's more like Rust, and it doesn't really matter. Or I can handle errors like Go would be like a tuple. Or I can handle errors like C++ typically does it, which is exceptions. Now, I'm not a fan of exceptions. I actually don't think they're good. But I don't think you should have 2 ways to handle errors in your code base. It sounds like it's more flexible, but it's just more confusing. And it relies more on template magic than it really deserves. Unless it's some compile time thing. It may just be some compile time thing, which I still think is stupid, to be fair, to be frank. But I think that'd be a little bit better if it's just like hash defiance, right? But it still would result in some really weird looking signatures, really hard to read code, because you'd have like 1,000 hash defines everywhere, change your return types, everything. And I think change your return types based upon some compiler flag would be like really like an interesting choice. And so really, I think this is what it originates with, is basically my problem. And then you have the fact that, in most days, using things like new are massively discouraged, new such delete, for good reason, right? Because the better way is to handle it with things like, unique pointer, but shared pointer. But there's still plenty of cases where these things aren't suitable. And so you end up needing to use pointers anyway. So this doesn't really solve all the issues, right? And Rust kind of handles, I think, is much better, because I think Rust kind of I don't know. I think in Rust, the way it handles references is much better than C++. I don't love the borrow check in Rust. I think the borrow check in Rust is really, really bad. Mainly because I don't actually think it solves the problem they think they solve. And I mean, I'm putting all languages on blast today, I guess. But what I mean by that is that I think you set out to solve a problem, right? And I think in this case, the problem they try to solve is, memory safety, right? And they're like, oh, for memory safety, what we have to make sure is that you only loan an object once, right? Or you can have multiple read access to an object, but only one write access. And it's a good idea. And it solves some problems. It solves iterated invalidation. Like, that's a big deal. This is a huge deal for C++. This happens all the time for C++ code bases, right? It doesn't sound like it happens, but it does. And it solves it. But what else does it solve? And it solves a few other things like this, small issues here and there, but it doesn't really solve the memory issue. Because most of the time, people have memory issues in places where Rust still doesn't have memory safety, right? So most of the memory issues that people have are in custom written containers. I would say, at least from my experience. Most people know how to use unique pointer. So most, references to objects are unique pointer and they are safe, right? I want to say it's impossible to break your unique pointers to memory safety, but I'm sure it's possible. It's just not typical. It would be very weird code to do that. And for SharePoint, it's pretty. I would even go as far as to maybe say it's impossible for SharePoint, right? And so in these cases, C++ is pretty memory safe. It really is just things like iterate and validation, use after free, that sort of stuff that C++ doesn't do that well at. The case where you move a unique pointer and then you try to use the old one, right? This is a big deal as well. And so I'm not saying that C++ has solved these issues and Rust hasn't really solved any issues. I'm just saying these are really fundamentally the major issues that Rust solves. It doesn't solve memory safety as a concept. It solves these kind of niche cases due to borrowing and moving, right? And it solves them well, granted, but it still just solves these cases. It doesn't solve things like cases where you need to use very complicated, unsafe memory code. Because the fact of the matter is that Rust has had multiple issues. I mean, don't kid ourselves. Rust has multiple issues all the time from code that was written in unsafe memory code, unsafe code blocks, right? That is just unsound. That has bugs. I mean, there was standard library. There was a blog post written about it probably a year ago now. They're saying, look at these like 5 standard library functions that all have all these unsafe bugs. Right? The fact of the matter is that we're humans and we're going to make mistakes wherever you let us. And Rust doesn't help you that well in multi-threading. When you're in multi-threading, it helps you a little with sync and send. It helps you a little with things like Arc and RC, but it really doesn't perfectly help you. It doesn't do enough. It doesn't really help you prove databases aren't a real thing. Like it says it does, there's plenty of cases where it can't. And so you kind of still a bit on your own. And this isn't a bad thing. It's just these two issues it doesn't solve. And so the borrow checker really is just for borrowing. It's not a memory safe checker. It's just to check that you borrow things and you return things back. It doesn't check for memory corruption. It doesn't check for using an unsafe pointer because you think it's faster, then you index by some random index, which happens, and then it's wrong, or you underflow and overflow causing problems. I mean, typically those will raise exceptions, but whatever. So I think at the end of the day, the problems it solves aren't necessarily the problems that I think people think it solves. Using a borrow checker doesn't make Rust safe. It just makes it safer. And so I actually think one of the reasons why I quite like Rust for fast code nowadays, or for this kind of like high performance stuff, is not because it solves any problems that C++ doesn't solve. Because it really doesn't solve that much. Like these issues are issues, but these two are very easy to find through Valgrind. This is pretty much a use after free, use after move, I guess. And it's also pretty easy to find through Valgrind. You just disable your realloc, right? And then you make it so that, well, you don't disable your realloc, but you basically make it so your realloc does this. It frees the old memory. It like does these steps every single time. So this is what you do to test for iterate and validation, basically. I mean, you don't have to do it this way, but every time you kind of like this won't test for everything, but for vectors this will test it for, right? Which is the most common case of iterative validation, but even hash maps and things. So every time you would do an action that would invalidate an iterator, like removing, adding, whatever, and that kind of operations changes the array, which typically invokes like realloc. I mean, removing, right? But typically adding is the one that does. And so what you do is you basically have it so you effectively always reallocate new memory, right? And then you copy across the old one, and then you free the old one. Now, this only typically happens with realloc if there's not enough space to just extend the memory, but you don't want to do that. When you're testing for iterative and validation stuff, you don't want to do that. You always reallocate. Why? Because it means that then therefore you have a use after free. That's your problem now. If you're using like the alt pointer, that Valgrind will pick up and stuff like that. So I think this is really what it comes down to, is that sort of thing. And it's pretty easy to replace a method like that across the entire program, or even like a section of the program. Anyway, so the second point I have with it is this whole issue of the 0-day thing. It's hard to install C++. It's really hard on Mac. Linux is fine. Linux has always been fine to install C++. It's hard on Mac. It's reasonably hard on Windows, unless you're using MSPC, and it's just a pain. And the package manager is a huge pain. So an example like this code here, right? Anyway, interesting. I have what am I looking for? A CMake list. I have a CMake list, which is my compiler thing here, right? And there's a bunch of stuff here, interpreter common, all this kind of stuff, right? And all this code gets compiled to produce an output that then runs. And part of this is libraries. Now, in this program here, I literally didn't manage libraries. I just said, okay, you want to install this, you'll git clone these 6 libraries, or chuck the HPV file in the lib folder, and then it will compile. That's not a good way of handling it. But the fact of the matter is that choosing a package manager when this was written, which is, by the way, in 2019 or something, it's 2 years ago, but it's 2.5 years. It was 2019 August. So that would be 3 years ago. It depends on what file you're looking at, obviously, right? You can see here, it says 2 years ago, but for like AST, maybe we'll say 3. I don't know, apparently not. Anyway, it doesn't even matter. But the thing about this is that what you end up with is a toolchain that's very complicated. CMake is really complex for big projects. My CMake there is simple, but it can get really complex really quickly. Conan or VC package or whatever one you want of the month for your package managers, they're all okay, but they all have flaws. And they're not integrated, which means you spend a huge amount of time preparing them and updating them and make them nice and all that kind of stuff. So fundamentally, I think, to sum up this main point here, the problem I have with C++ in a compiler, and I mean, I say this is a really big issue, but it really isn't. You can definitely use C++ for a compiler. But the problem really comes down to the fact that it's interesting. Anyway, it's slow to compile. It's very bloated as a standard library. There's the lack of a package manager. Templates are not a mistake, but were kind of brought too far. Things like constant expression is amazing in C++, right? Really, really good. And solve a lot of what templates needed to solve at the time better than templates do sometimes. So you almost want constant expression and concepts to be required features in templates. I mean, constant expression not so much, but you almost want concepts or constraints to be required things. Say, hey, I want a pessimistic thing. I want to know exactly what types are possible for this. And I think if you had that, I would be much more inclined to choose C++. I'd probably still end up rewriting a lot of the standard library in its current state. Maybe it's a bit better if I had all the optimism or the pessimism. But I still think it would be better. If you look at something like Rust, right? It's a whole lot cleaner. But it's pretty much the same code. There really isn't that much difference at a raw level between the two. This is a parser. for an atom. This is a parser for an atom. This code compared to this code really doesn't have that much of a difference. I mean, this code here could use a switch statement. But really, left parentheses, pop the left parentheses, pass the expression. If there's no expression, return, propagate the null operation, right? Same thing as option, right? There really isn't a difference here. If there isn't, then make a unique atom from that line range position and then consume the right parentheses. Right? Fix me. And so in Rust, I really kind of reject the claim that Rust code looks nicer, because I think it comes down to this. Code looks bad if you write it bad. And I think you can write some really clean and nice looking code regardless what language you're in. Not all this code is really clean, but this code at least is reasonably easy to break up. You can look at any one function and kind of go, yeah, okay, this makes sense. And you can look at the AST and break it down and go, yep, no, this stuff is reasonably easy to understand and read. And the same thing with Rust. So I think when you're comparing the languages at that level, there really isn't a reason to choose Rust over C++. But when you're comparing the languages, template systems, their libraries, the safety, and all that kind of stuff, I don't see C++ as a necessarily great language to choose one in. Right? For me. Because I think I would spend so much time fighting with the language, I would spend so little time writing code. As I say, I've spent 42 minutes complaining about a language. And so I think, hopefully that kind of, cleans up some of these things. And I think it's interesting because I think I've been writing programs for a while, definitely many programs for a very long time. And languages for quite a long time too. And at the end, honestly, there's very little difference between most languages. But the things that do make them different typically have a huge impact on how well I enjoy or like them, or how well I think they perform. So let's kind of clean this all up and kind of lead towards kind of a resolution here. So, I say Rust is better in these cases here, or at least I prefer it. And even though I don't like the language itself in all cases, because I think some of it's too verbose, I think some of it's like a little hipster. I think some of the decisions they made are extreme, stuff like that. But I think at the end of the day, as I said before, it doesn't matter. Because what matters is it's clean, it's easy to read, people understand it, people love it, people want to commit on it. I think that's what matters. And if you want to choose this, go ahead. Right? Go ahead and write an AST in C++. Go and use variant and have really annoying issues because variant produces really confusing compile errors. But it's okay. You can do that. Yeah, so that's pretty much it. If I had to write a game though, I'd probably write it in C++. I think maybe, I don't know. So hopefully that was somewhat interesting and kind of giving you some context behind why I prefer certain languages over other languages and why I chose C++ for this project, and kind of maybe hopefully getting you excited for tomorrow and so stuff like that. So we're gonna start. I don't know if we're gonna work on the compiler tomorrow. I still haven't really decided. I kind of like leaving things to how I feel. I'm kind of really excited to touch it, but also I'm kind of scared, I guess is the way I would put it. Because it's been a while, so I don't really want to spend too much time playing around with it and figuring out how it works and getting really confused. I've already cleaned up some things, and so I'm pretty excited about it, and I want to talk a bit more. I want to do some more videos about my plans for the language and stuff like that. So I'm wondering whether or not I kind of do those before I go into anything. But I think what I'll do is I'll start off with a bit of compile time for maybe an hour. And if I'm vibing it, I'll keep going. Else I'll shift into maybe something else. I am considering actually writing some C++, breaking my own rule. But I do kind of want to write a game. And so I've said that before, you know, show off the idea and stuff. But the thing about that game is I want it to be online. And so if I want it to be online, it kind of does fit a game for something like Unity and stuff like that. Like that's a better use of my time, but I don't really care about my time. I just care about having fun. So we'll see how that stuff works out. And hopefully it's really interesting and hopefully you'll enjoy it a lot. And yeah, I don't know, I definitely will. So I will see you guys later. This is a bit of a long first video. I was trying to keep it short, but I think the it deserves the kind of time and effort that goes into explaining this stuff and kind of understanding my position here, because I think this sets us up for the rest of this. Awesome.